So you are ready, Mike?
Yeah.
Okay, so let me introduce you and then welcome everybody. It's very nice. We're very happy to have today Mike Blake from University of Bristol. You probably everyone knows him, and he will tell us about systems of maximal quantum chaos.
Okay,
go ahead.
Thanks. Let me just share my screen then. I'm gonna do this as sort of a Blackboard talk on my iPad. So can everyone see my my whiteboard now, I guess?
Yes.
Great. So thanks very much for the invitation and chance to come tell you about some of the work we've been doing. So what I'm going to talk about today is some new results we have on continuing an old program of work I've been involved in over the last several years, in which we started looking at connections between this new phenomenon of many-body quantum chaos and how it was connected to hydrodynamics. So in particular, a couple of years ago, we proposed an effective theory approach to describing this chaos based on hydrodynamics. And I want to tell you about some new results that we found within this framework, in particular on how it's related to maximally chaotic systems, and also some new signatures that really distinguish that this scrambling and chaos in maximally chaotic systems seems quite different in nature to in other types of system. And that's what I'll hope to explain in this talk. Okay, good. So as I should say, this is based on work with Hong Liu, who I'm sure you all know. So I'm going to start with a general introduction, but if you please just stop and interrupt at any point, because I'll go quite quickly at the start and then slow down, I think, as we go on at various points, because I want to get to some, I've got quite a bit to introduce. Okay. So the basic point is that what we've been interested in understanding over the last few years are these signatures of chaos in a quantum many-body system. So of course, chaos in classical systems and in single particle quantum mechanics has been studied for a long time, and it's always been a very hard problem to try and understand what that could mean in a many-body setting. And people have, over the last few years, made some progress in characterizing chaos in these systems, essentially by asking about the dynamics of operators in the Heisenberg picture. So in particular, if you have a simple few-body operator in the Heisenberg picture, it will start off as a simple operator containing a few degrees of freedom, but if you evolve it in time, it becomes more and more complicated, becomes a more increasingly large and many-body operator as it grows. And so the question, what people are doing is essentially probing that growth of the operator in time through various probes. So the probe you're perhaps most familiar with is this so-called out-of-time ordered correlation function you may have heard of. So there's been a large recent interest in these out-of-time ordered correlation functions as a probe of chaos in these. And the idea is it's a probe that is defined in the many-body setting. Okay. So in particular, the systems I'll talk about today are all going to be large N systems, so systems which have a large on-site Hilbert space dimension. But in general, you can look at this in other systems as well. And the types of correlation functions people are interested in, one type would be to ask about, suppose I take some operator W and some operator V, and let's assume that at some time t equals 0, they're both just some simple operators, like a few-body operator of Pauli spin. Well, at time t equals 0, this commutator will be small, but as I evolve W in time and it becomes increasingly more complicated, the squares of commutators of operators grows. And in these large N systems, so things like SYK models and holographic systems, or just large N quantum field theories, typically you find that this correlation function will start out as being suppressed. It's very small, proportional to 1 over n, where n is the number of degrees of freedom. And then it will grow exponentially in time, which gives you this definition of an exponent, the Lyapunov exponent, that's now an analog of the classical Lyapunov exponent of a chaotic classical system, but that applies to a many-body quantum system. So what people have been interested in doing is computing these correlation functions in a variety of systems. And one of the deepest aspects or most interesting aspects of this many-body chaos is that at finite temperature, so these are finite temperature correlation functions, this quantum Lyapunov exponent cannot become arbitrarily large, but is bounded essentially by the temperature of your system, okay, in some units. Okay, good. So people have studied these in a variety of systems, for instance, holographic systems and SYK models, as I've mentioned. And the basic question I want to ask here is, what is it that is so special about systems that actually saturate this bound? So if we have a system that's so-called maximally chaotic, it has this largest value of the quantum Lyapunov exponent at finite temperature, then what's special about that system, or is it special, and what defines these maximally chaotic systems? So the basic motivation is what is special for this talk about systems that saturate this bound. And examples of such systems are SYK models at strong coupling or holographic systems dual to gravity, classical gravity. Okay. And a partial vague answer or potential answer, which is sort of the framework behind all of this work, and for now I'm just meaning this in a very general term, not something any specific, is that this chaos essentially has a hydrodynamic origin. So in particular, if you look at, for instance, these SYK models at strong coupling, when they're maximally chaotic, or these holographic systems, it's easy to, well, relatively easy to see from those calculations that this exponential behavior can be understood as coming from interactions between these operators where they interact via exchanging stress tensor, the stress tensor essentially. So this exponential behavior essentially originates from the stress tensor dynamics of your theory. And at the moment, that's really all I mean by this idea that chaos is hydrodynamic. Much of this work is an attempt to make this precise. Okay. So here I mean it originates from interactions of these operators with a collective with the stress tensor. Okay. So let me write that as ST. Okay. So for instance, in holography, it's because if you have a maximally chaotic system, that's when you have a theory dual to classical gravity, it's the gravitational interaction that gives rise to this exponential behavior in the holographic picture is through gravitational interaction. And we know that that's coming from the stress tensor in the boundary quantum system. Okay. So this observation that in many of these maximally chaotic systems, it was the stress tensor interactions that were leading to this exponential behavior motivated us to try and build an effective theory approach to describing chaos, because we know how to describe the dynamics of a stress tensor in a quantum system, okay? So in particular, if we have let's say we have a classical system, you know that you would normally describe, at least at late times and on long distances, the dynamics of the stress tensor using hydrodynamics. Well, more recently, there's been a lot of work in elevating that classical hydrodynamics to a full quantum theory. Okay, and so this was work done by Hong Liu and by other groups as well. Lots of interest in formulating this exact theory of quantum hydrodynamics. And in 2018, we used this theory of quantum hydrodynamics to propose an effective field theory description of chaos, okay, motivated by these results. So in 2018, we proposed a general chaos EFT based on this quantum hydrodynamics that had been previously developed. And in our work, we proposed we essentially just worked out what you would need, what conditions and what form such an effective theory would take, and showed that it was, and showed that you could build a description of chaos using this effective theory, as I'll explain later. But one thing I want to say is, as well as this sort of abstract general effective theory approach we proposed, there are actually several very explicit constructions of effective theories of chaos that are essentially this quantum hydrodynamic theory we were proposing. Okay. So there are several explicit examples in which you can actually write down such an effective theory. So the simplest one is the SYK model, that's strong coupling. You have the Schwarzian theory that describes an effective theory that gives rise to this chaos behavior. And that Schwarzian theory is precisely a hydrodynamic description of the stress tensor. So it's the simplest case of this quantum hydrodynamics. And really what we were doing was saying that that should be generalized to any to arbitrary quantum systems. So after our paper, Moshe Rosali and Felix Hale and collaborators did some really impressive work in which they worked out these types of effective theories for 1 + 1 dimensional CFTs and for CFTs, high dimensional CFTs in Rindler space, in which you have these reparameterization modes, which are essentially these hydrodynamic modes and describe the stress tensor. So there are some examples of this theory, which I'll discuss a little bit later. And also it predicted or led to a new phenomenon known as pole skipping, which has been investigated in many papers since. So this idea of pole skipping is that if you have an effective theory in which the stress tensor dynamics are giving you this exponential behavior, then the form of this out-of-time ordered correlation function should have something to do with, should leave some imprint in the stress tensor. And it leaves a very specific imprint, which is what we call pole skipping. And that's something that's been studied in and proven for very general holographic systems. Okay. So I don't, in this talk, want to mention that anymore because I want to discuss some new things we found. And these, I think, are rather interesting. So further work has revealed 2 new features of this theory. Okay, so the first is that when we first proposed this theory, we weren't sure, okay, it was motivated by maximally chaotic systems, but we weren't sure if it was limited to those systems or could, in principle, describe others. We now know that actually self-consistency of the theory forces that the Lyapunov exponent is maximal. So this hydrodynamic theory of chaos is, by consistency, a theory of maximally chaotic systems. And so the first thing I want to put forward is this is a signature. This is really one of the defining features of maximal chaos, is this hydrodynamic origin of chaos. And the second I want to tell you about is a bit more surprising. The first, I think people expected. The second is that in this hydro EFT, there is a suppression of the chaos behavior in what are called commutator squares. So this will sound a little technical, but I will explain what's going on here towards the end of this talk, and I think it's very important. So the basic point is normally when you write down these commutator squares that I've indicated on this side, everyone always writes them down as having this functional form of being proportional to 1/n times e to the lambda t. Okay, and the reason we do this normally is that what people normally calculate is the out-of-time ordered correlation function, in which we have WB, WV, and it's true that in, for instance, holographic systems, this will be proportional to 1/n e to the lambda t, where lambda, if you have a theory dual to gravity, is the maximal result. However, the thing that will turn out happens, and does indeed happen in holographic systems, is this expression here for the exponential behavior for the commutator squares is not quite right. In fact, it's quite misleading. In particular, what you find is if you computed this object in a holographic theory dual just to classical gravity, you would find that that answer is exactly 0. Okay, so this commutator square is actually identically 0 in classical gravity. And the reason is it's the sum of this out-of-time ordered, it's roughly speaking the sum of this out-of-time ordered correlation function I've drawn and another one in which you swap the V's and W's around. And what you find in holographic systems and in general in any maximally chaotic system is actually, as I'll explain later, that both these out-of-time ordered correlation functions have exponential behavior, but at leading order in 1/n, they precisely cancel against each other in this commutator square. And so this is something that only happens for maximally chaotic systems, as I'll explain. it emerges automatically as a prediction of this hydrodynamic effective theory. And so that's what I'll discuss in the second part of the talk. Okay, good. So I now want to go and review this effective theory before, and I'm not gonna go through in any great detail any of the maths because it's not really relevant. I want to just explain the philosophy and then the details for how we get these new results before moving on. So if I go a little quick here, please don't worry about the details, but do stop me if something's not clear. So what's the basic point? Well, as I said at the start, the basic thing this chaos is probing is the growth or scrambling of operators, which is how they evolve in time in the Heisenberg picture from a simple few-body operator to some complicated many-body operator. And what this hydrodynamic theory's basic idea is that we want to describe this as the build-up of, as our operator evolves, in terms of being we want to describe our operator as a bare operator, so some few-body bare operator, but that builds up a cloud, a hydrodynamic cloud, which describes how its evolution in the space of degrees of freedom as it becomes a many-body operator. So it couples to some collective many-body mode, okay? So we have that this growth scrambling of the operator is essentially described, and this is really just words. There's a mathematical framework. Mathematically, we define more precisely what we mean, but heuristically, you can think of it as some bare operator building up some cloud of hydrodynamic modes describing its growth. So in particular, we have our operator V, which we can think of as consisting of a bare operator, which I'll call V hat, which is a few-body operator, and then it's coupled to this hydrodynamic mode, which I'll call some collective field sigma of t. Okay, so we have some bare operator, and then it's building up some cloud described by its coupling to this field sigma of t. Okay. So the first step is that we assume there's that we can describe this as some coupling to a collective mode. The second step is that this is not just any collective mode, but we identify it with the collective degrees of freedom that describe energy dynamics in hydrodynamics. So we identify sigma of t, the collective field describing the collective field in our chaos EFT, as the collective degree of freedom associated in this quantum hydrodynamics associated to energy conservation. So a few comments are in order here. Here and in my notation and throughout, I'm going to describe the theory in 0+1 dimensions for simplicity, because otherwise it will become much more complicated. In the second point, what do I mean by this? Well, you're probably familiar from normal hydrodynamics that if I want to describe the dynamics of the stress tensor, I do that by parameterizing it in terms of some degrees of freedom. So for instance, normally in hydrodynamics, these are a local temperature and a local fluid velocity. Okay, so all I mean is we're doing the same thing here in this quantum hydrodynamics. You again introduce these degrees of freedom. You again parameterize the stress tensor in terms of, in terms of some fields like a local fluid velocity. In 0+1 dimensions, the only field you need to introduce to parameterize the energy dynamics is this field sigma of t, which essentially is essentially a reparameterization of time, and it describes the fluid time sigma as a function of the physical time t. And you use that to write down and construct your theory of hydrodynamics. Okay. So this sigma field is a time reparameterization field, or it's a fluid time. Okay, good. So how does this work? Well, this quantum hydrodynamic theory that had been developed previously by Hong and collaborators and also by other groups, basically gives you an effective, gives you some rules for constructing an effective action to describe this field, and then on how to calculate correlation functions of the stress tensor. So in particular, we have some action that describes this field sigma of t, and this is just the hydrodynamic effective action from which you can compute hydrodynamic correlation functions. Okay. So the dynamics of sigma of t are described by some effective action, and this is as a full quantum theory. There is just a quantum field theory action describing this field. Okay, good. So the first thing, one thing I want to emphasize though is, as in normal hydrodynamics, and this is the key, this field sigma of t is not itself the object we're interested in. Okay, we want to calculate correlation functions of operators. So in the context of hydrodynamics, that what we need to compute what we want to compute are the correlation functions of the stress tensor. Sigma is just a variable we introduce in our path integral to help us do that. It isn't itself directly physical. Okay. So this is like saying the fluid velocity itself is not a physical observable in hydrodynamics. You ultimately want to compute stress tensor correlation functions. So stress tensor correlation functions can be computed from sigma of t. Okay, and how do we do that? Well, in normal fluid dynamics, it's kind of the same. In quantum hydrodynamics, there are some constitutive relations. Let me just write constitutive relations that relate the stress tensor to sigma of t. We have some action for sigma, and by using the constitutive relations, we can then compute correlation functions of the stress tensor as well. Okay, and ultimately, those are what we're interested in if we're just doing hydrodynamics. Okay, good. So far, I haven't really told you how you can use this to construct chaos. But the basic point is that it's possible to use this type of hydrodynamic effective action to consistently write down a theory that has exponentially growing modes, but that they're not a symmetry. They're not an instability. Okay. So how does this work? Well, in equilibrium, you have a situation where the fluid is at rest. So the fluid time is just the physical time. And the key point is that if you impose, as I said, is that it's possible. And the way you do this is to impose some symmetry on this effective action. And if you impose a symmetry, you can find that there are actions for which sigma of t can consistently have exponentially growing pieces. So you can construct a theory in which this field in the hydrodynamic description has exponentially growing modes, which ultimately are going to be the origin of this exponential behavior. Okay. So in particular, what we can do is we can consider this field epsilon of t, which describes the difference between our fluid time and the physical time. And if you pick certain actions or impose a symmetry on the action, you find you can have solutions in which this is growing exponentially. And the idea is that because of the coupling of operators to this field, that's going to give me this exponential behavior in correlation functions eventually. Okay, good. And so at this point, you probably would have a question, which is, okay, why is this allowed? Normally, if I have a field that has just exponentially growing modes, then I would say that's an instability of my system. And so this is why it's important that this sigma field itself is not directly physical. It's the stress tensor correlation functions that are physical. And the point is that as a result of this symmetry we impose, that's what I mean by consistently, if you impose this symmetry, you find that actually the stress tensor correlation functions do not have any exponentially growing pieces. They're perfectly consistent with all rules you would want them to obey. They satisfy fluctuation dissipation theorems. They have no exponential growth. It's perfectly consistent for this sigma field to have an exponentially growing mode because it's not a physical degree of freedom. It's just a field you integrate in order to parameterize the stress tensor dynamics. Okay, so this is not an instability of hydrodynamics. And this is why hydrodynamics it allows you to formulate this effective theory because it has this field that these degrees of freedom in it that we know and have known for a long time, but they are not themselves directly physical. So stress tensor correlation functions have no exponential pieces, no exponentially growing pieces, and are consistent, e.g. with the fluctuation dissipation theorems, etc. you would want them to obey. Okay, good. So we're getting there. I just need to remind you of a couple, tell you of a couple more facts about how we get this, about now how once we've got this exponential mode in sigma, how that results in this behavior in the out of time ordered correlation functions. And as I said, the basic point, as just because we have some coupling of these operators to sigma, we're going to expect this exponential behavior to filter through into correlation functions of our operators. So in particular, at leading order in 1 over n, the way in which you compute out of order time, the way in which you compute 4-point functions of these few body operators. Okay, so we take some operators v and w, which, as I've said, have some coupling to this hydrodynamic mode, and they're just if you have some coupling to them, what you find is that the leading diagrams just turn out to correspond to some tree-level diagrams in which they exchange this sigma field. Okay, so to leading order in 1 over n, what do we get? Well, the diagrams look something like this. Our two V operators come together and form a vertex that couples to this hydrodynamic field. And similarly, our two W operators come together and form a vertex, which couples to our hydrodynamic mode. And they exchange this field, sigma, which has this exponentially growing piece. And that's ultimately where we're going to get our exponential behavior from. Okay. Good. So there's one important point to explain, though, about this, because it's going to be the origin of why this theory ends up being only consistent for maximal chaos. And that's that at the moment, these types of diagram actually contribute both to so-called time-ordered correlation functions and out-of-time ordered correlation functions. So in particular, we get these types of diagram both for, so the only difference between so-called time-ordered correlation functions. So these are the normal types of correlation function that until a few years ago, we'd just be the only things we were really interested in. So these are things such as, for instance, we can consider, actually, let me give this a name. Let's call this G4. G to start, G will be a time-ordered correlation function, and 4 because it's a 4-point function. Let me just consider something like VW, VW, V0, V again, sorry. So this is time ordered because if I commute the operators, it looks that I could have them all increasing in time. This is the type of correlation function we'd be used to calculating, and that certainly should never show any type of exponential growth with time. If such a correlation function did, then that would of course be an instability. These correlation functions should not have any exponential growth. The exponential growth should only be in the out of time ordered correlation functions, which I will call H. And these are the ones where we alternate between going an operator that's forward in time and an operator that's at time t equals 0. Okay. So there's a potential problem here in that we have these diagrams contributing to both of these. Okay, and the only difference is the vertex structure. Okay, so there's a slightly different structure in these vertex for the time-ordered correlation functions as there is for the out-of-time ordered correlation functions. Okay, so we've got a potential worry in that we want exponential behavior in the out-of-time ordered correlation functions, which clearly we're going to get from these types of diagram, but we don't want it in the time-ordered correlation functions. So how does this theory get around that? Well, the answer is quite simple. It's just that the vertex for the time-ordered correlation functions can very naturally be extended can very naturally be made invariant under this exponential mode, so it doesn't see the exponential mode. Essentially, you can impose a symmetry on the vertex of the time-ordered correlation functions so that the exponential piece doesn't doesn't essentially appear in this time-ordered one. Okay. So basically, by a certain choice of coupling of operators to this field, and this is actually exactly what happens in, for instance, SYK, by extending the symmetry of the theory to the coupling in a natural way of operators to sigma. One finds that G4, the time-ordered correlation functions have no exponential pieces. Okay, but it's important you have to impose a condition to do that. And then you find that, okay, even though this condition causes there to be no exponential growth in the time-ordered ones, it doesn't cancel out the exponential growth in the out-of-time-ordered ones, and so we're able to build this description of chaos. So you find, in fact, if you compute the difference between this out-of-time-ordered correlation function H4 and the time-ordered one G4 in this theory, then let me put some squiggles in because what I'm going to write is schematic. This essentially can be thought of as the two-point function of this sigma field. So epsilon is the linearized sigma field about equilibrium. And if you compute this because this two-point function is going to have an exponential mode, you get that the out-of-time ordered correlation function grows exponentially in time, and there's some coefficient proportional to 1 over n, where that n is the number, again, of is number of degrees of freedom. Okay, so this is the end of my summary of this theory, and the basic point I want to emphasize is that using this hydrodynamic theory, we get some exponential growth in H4, the out-of-time ordered correlation function, describing a chaotic system. However, there's no exponential growth in the time-ordered correlation functions, and ultimately, this H4, the form of the out-of-time ordered correlation functions, it comes from essentially the two-point function of this epsilon field. And so for those of you who've looked at pole skipping, that's why you get a connection between the stress tensor and the out-of-time ordered correlation function. The thing that's governing this out-of-time ordered correlation function is basically the two-point function of the epsilon field. The thing that's governing the stress tensor two-point function is the two-point function of the stress tensor, but they're related just through some constitutive relations, and so they're very, very closely related to one another, which is what leads to this the so-called pole skipping phenomenon. Okay, good. So now let me tell you about these two new features that we've done. So that was the status as of 2019. And in particular, at the time of doing this, it was unclear if this theory was consistent for any lambda, or this theory should work for any lambda or for lambda max, or just the maximal value of the Lyapunov exponent. So at the time, it was unclear if this theory could work for any value of this Lyapunov exponent. We didn't have any condition to fix the Lyapunov exponent in our theory. It seemed it could just be arbitrary. But naturally, one thinks, as I said at the start, that the examples in which we have a hydrodynamic origin of chaos, some stress tensor being responsible for chaos, are these maximal ones. And so we know, and so you might think that really this should just work for maximally chaotic systems. So I don't want to give the details of the proof of the maths of this now, but we can now actually prove that indeed it can only work for maximal chaos. Okay, and the reason for this is as follows. Essentially, it's this condition I specified here where I said that we had to impose this symmetry in order that there were no exponential pieces in the time-ordered correlation functions. Okay. So in order for our theory to be consistent, we had to get rid of that exponential growth in the time-ordered correlation functions. We were able to impose this symmetry, ensuring that that was the case. But it turns out that that symmetry is only consistent with the fluctuation dissipation theorem if you have maximal chaos. Okay. So in particular, we want to, if you look at the structure of this vertex, the vertex involves the coupling of essentially two V operators coming together and coupling to this sigma field. And so you find that this symmetry condition involves the 2-point function of this V operator. Okay.
So, sorry, Mike. Yeah. One question. Maybe I missed it, but what is the symmetry you are imposing?
So I basically, there's a condition on, it's really some condition on this form of the coupling.
I see.
I can't easily write it down. It would take 20 minutes to write it down, basically.
Okay.
I can't easily write it down. So that's basically the problem. I can't easily write it down, but there's some condition on the coupling I have to impose. And that condition turns out to be only consistent if the theory is maximally chaotic. And the reason is that condition turns out to be a condition that relates the coupling I impose. It depends on the coupling I impose and the 2-point function of the V operator. And if I use the fact that the 2-point function of the V operator must satisfy the fluctuation dissipation theorem, I find that the Lyapunov exponent has to be maximal in order for that to be consistent, basically. So it's a little hard to explain without writing down explicitly the equation that describes that means the symmetry, but that is the condition on the coupling. But I don't think it would be very instructive to do so. So I think maybe I'll just say it is only that condition that we had to impose is only consistent for maximal chaos.
So can I just ask a related question?
Yeah.
So is that a generic procedure that you can use for a given theory and obtain the same result, or?
So you'd need to construct this. You need to explicitly know what this effective action is. You'd need to construct. In principle, you could construct this effective action, but you need to know what to use it in a given theory. You need to know what the effective action is, and there are examples of that where you do. In general, there's not. For other theories, more generally, it does still lead to some predictions that you can test in other theories. For instance, this pole skipping phenomenon is one, which is a prediction of essentially a self-consistency prediction again of this theory. And then you can test that in all sorts of other systems, like holographic systems, even though you can't easily construct the effective theory. So what I'm saying is it's quite hard to actually determine the effective theory for a given system. But let's say we think this effective theory does exist, we get then lots of even though it's hard to construct it explicitly, there are still predictions of the theory.
I have also a question, Mike, sorry.
Yeah.
Let us suppose we have a theory, but we are not aware of whether the theory is maximally chaotic or not.
Yeah.
Okay, then how to understand the answer? Is it necessary to compute the Lyapunov exponent, or, for example, we can look for some symmetry like what you're using in your theory or not?
So if you don't know if it's maximally chaotic or not, I'll actually end by giving well, there are some features of maximally chaotic systems that I'll end with a condition that could distinguish between them without you having to compute a Lyapunov exponent, yeah, I'm not quite sure I understand the question in that. If you had this effective action, well, ultimately I think I would say that. Yeah, let me say, I don't know a good answer to that question, a sharp way to distinguish them beyond immediately just without computing something, without looking at, there's going to be something I'll tell you at the end of this talk that would be a way of distinguishing them if you don't know if it's maximally chaotic or not.
Okay, thanks.
Okay, so let me just say we can, we now can prove that the condition on the vertices such that exponential growth does not appear in time-ordered correlation functions is only consistent with the fluctuation dissipation theorem for maximal chaos. Okay. So, okay, I know I'm not explaining that particularly well or why that's true, but maybe just take it. It's a somewhat technical condition arising out of this theory, that this theory is really only a theory of maximal chaos. And in particular, I think based on the fact that in lots of systems, we know that the stress tensor is responsible for chaos when they're maximal, and when they're not maximal, then they have other contributions to the out of time ordered correlation functions coming from higher spin operators. You shouldn't expect really this to work for non-maximal chaos. The stress tensor, and you should think of this hydrodynamic description as being one of the defining features, I think, of maximal chaos, at least in the sense that it's the stress tensor that parameterizes that's responsible for chaos in those systems. Okay. So the reason I've slightly rushed over that is I'd like to spend a bit more time talking about the second feature, which I think is slightly more surprising and newer, that I think people maybe would have anticipated. The thing that I think is more surprising is this business about the commutator squared. So the second new feature which I want to discuss is this suppression of commutator squares. So I'm going to introduce, to be precise, some notation. So let's consider the following correlation function, which I'll call C, which is just, I take the commutator of W and V, but I'm going to just at the moment allow arbitrary times. So it's what I wrote down on the first slide, the square of the commutator with W and V, but I'm going to allow different times for each of the operators in this square. And the configuration I wrote down on the first slide was where T1 and T2 were 0 and T3 and T4 were T. So with T much bigger than 0 compared to the temperature, inverse temperature. But that's just allow T1, T2, T3, T4 to be to be arbitrary, but approximately 0 and T. So the thing I said on the first slide was that this theory, explaining the introduction, was that this theory is actually predicts a suppression of these of the commutator squares. So in particular, I can decompose this if I write this out, expand this out, and just multiply out the brackets. I get 4 terms, 2 of which are out of time ordered, which are what I'm calling the H's, and 2 are time ordered. And if I explicitly write them out, H4 is just WV, WV, and H4 tilde is VW, okay, VW. And then G4 and G4 tilde are just the time ordered correlation functions with some of the operators swapped around. Okay, so this is just expanding some brackets. So hopefully it's the details of this are not so important. Sorry, I've got this last one wrong. The W should be on the outside. Okay. So the point is, it's the sum of 2 out of time ordered correlation functions, and for a sum of 4 correlation functions, 2 are out of time ordered correlation functions, 2 are time ordered. And what I said earlier is that if in this theory you compute the difference between this H4 and G4, the time ordered and out of time ordered correlation functions, okay, you get this commutator of the epsilon field, which was exponentially growing in time. And if you compute these other 2 in this theory, you find it's exactly equal and opposite to the line above. Exactly. Okay. So here I'm not even assuming that these terms are necessarily exponentially growing in time or anything. Just any type of theory like this in which you assume coupling between operators and some collective mode, and then you try and write down correlation functions using tree level diagrams, you will find that this is true. And so this means that this correlation function at leading order in 1 over n of these commutator squares is identically 0 in this theory. Okay, identically. Okay. And also this is true if you consider analytically separating the commutators in imaginary time by some amount theta. You'll again find, so if you consider correlation functions where you have omega w, the first commutator, sorry, this should be a T2. If you separate them in time, you will again find that this is 0 in this theory automatically. Okay. So when we first saw this, we thought this was really bad news because this sounds very bad. Because, as I said at the start of this talk, if you have a chaotic system, these correlation functions you think are supposed to show this type of exponential growth that we introduced at the start. People write this down in all sorts of papers at the start as being the form of the exponential growth. And I've just shown you that in our effective theory of chaos, okay, then this is identically 0. Okay. So what's the point? Well, the point is it turns out that these are actually the same thing. Okay, and this is this feature that this commutator squared vanishes in our maximally chaotic system is not a coincidence. Okay, but is actually a general thing that happens in all maximally chaotic systems. And so it's emerging as a prediction of this effective theory. And it arises directly as a consequence of some type of effective theory where you couple operators to modes, but it's actually something that is a fact about maximally chaotic systems, and I think really indicates that there's something very special about chaos in maximally chaotic systems. As I said at the start, what happens is that in maximally chaotic systems, these two out-of-time ordered correlation functions both have exponentially growing modes, but they're of equal and opposite. They're equal and opposite, and they cancel in the commutator squares. And so that's something that's not been, I think, discussed enough in the literature. It has in a few places, but is really a sort of special signature of maximal chaos, is that this commutator square is really, in a maximally chaotic system, will actually essentially vanish and doesn't show any exponential behavior, whereas each of these out-of-time ordered correlation functions do. Okay. And so I want to end the talk by just going through the literature again and giving you a couple of new results about what's known about these commutator squares and just stating some facts just to show you that this is actually a good thing. If you have our theory is maximally chaotic and it predicts this commutator square is 0, that's exactly what it should do. And actually, I think this. All of our arguments for why this is true are just really observations or based on analytic continuation. This is the only physical understanding, I think, of why this is true, is if it arises from this coupling to some collective Lorentzian mode. Okay, good. So I now want to end by reviewing the suppression of the commutator squares in various, what's known about them in various examples. And the point is that this does vanish in maximally chaotic systems. It doesn't, and it being non-zero is a measure of how far away you are from maximal chaos. Okay, that's what this is. Good. And I should say, and I will discuss this in a second, but I'm not the first person to have observed this. It's just Kitaev has discussed this in some talks in the past and briefly in some of his work. But I'm going to try and make this much more explicit because this effective theory approach really forces you to take this, I think, very seriously. Okay, because it's automatic. So the thing I want to end on is that this suppression of the commutator squares is a signature. It's in fact not a coincidence, but it's actually one of the defining signatures, I think, of maximal chaos, and really indicates something different about maximal chaos to non-maximal chaos. That we need to understand, and it's implicit in some previous work, but I want to make it much more explicit. Okay, so I'm just going to go through and present essentially some facts about systems in which this vanishes. So the first fact is if you take the classic simplest case in which people can compute these out of time ordered correlation functions, and actually also these time ordered ones, these G's, is if you look at this Schwarzian theory that describes near ADS2 black holes, or also the Schwarzian sector of the SYK model, which is valid at strong coupling, where you can take the results from the papers by Maldacena, Stanford, and Yang, or by Stanford and Schenker, and you can analytically continue their Euclidean results to compute all these correlation functions, and you'll find that this correlation function is identically zero in the Schwarzian theory. So if you take the results from MSY, the Maldacena Stanford Yang paper on near ADS2 gravity, in which they computed these correlation functions in Euclidean correlation functions at least, and then if you analytically continue them, you'll find that although this wasn't discussed at the time, these squares of commutators identically vanish in the Schwarzian theory. They have some exponential modes, okay, describing the exponential bits that are the chaotic bits, but they have other functional forms in these correlation functions as well. That's just one piece of them. And everything completely cancels against these four correlation functions, and you get exactly zero as you'd expect from as you'd expect. Okay, and that's not a surprise because I said at the start, the Schwarzian theory is an example of this type of effective theory, but it's a fact that I don't think has been discussed. So the one place where I've seen this discussed a fair bit before is an argument due to Kitaev, in which he's given several talks on this and wrote some very nice work on it in his paper with Josephine Su, in which they talked about, in Kitaev's talk, he talked about what he called coherent scrambling. Essentially what Kitaev did was based on arguments associated with analytic, well, he had some physical intuition for this as well, but the mathematics that he presented was basically based on some arguments based on essentially analytic continuation, using that to essentially constrain the form of what form an out of time ordered correlation function could have in a 1 + 1D system. So in particular, Kitaev proposed an ansatz for out of time ordered correlation functions in, say, a generic 0 + 1 dimensional system, so a quantum mechanical system like SYK. And if I take my correlation function I've been considering, my out of time ordered correlation function, his ansatz, it looks quite complicated, but it has the following form, which is not too hard to understand. There's some overall real constant, which is C, just a constant, okay? Then there's some non-trivial phase related to the Lyapunov exponent. And this is the key player in this game. Then there's the exponential growth, which if you write it in terms, if you write it out, looks like this. So sorry, this should be a T2 at the end. So this is the exponentially growing term in the out of time ordered correlation function, but just written in a symmetric way. And then multiplying this are two so-called vertex functions that are not important for what I'm going to discuss. These are just essentially a bit like 2-point functions. They satisfy properties a 2-point function would do, like fluctuation dissipation theorem. They just depend on the difference between the 2v and the 2w operators. That they're not to do really with this chaos. They're just some vertices. Okay. So what's the important point? Well, the key thing in this equation is this phase. Everything else is either real or satisfies some reality condition, like a fluctuation dissipation theorem. And the important thing, the way this phase is fixed, is it's defined by saying if you analytically continue this correlation function, so you place the four operators evenly around a thermal circle, well, you know that that correlation function, it turns out it has to be real. So there's a constraint that this correlation function must become real if you place the operators, if you analytically continue it in a certain way. And that forces there to be some overall non-trivial phase related to the Lyapunov exponent. Okay. So from this, we want to calculate, this was his ansatz for H4. To calculate the commutator square, we also need to consider the other correlation function that appears, and the commutator square, remember, is the sum of these two. And the way you can do that is, it turns out that just by definition, there's a nice result, which is that this other correlation function in the commutator square is the complex conjugate of this one, where I also swap T1 and T2 and T3 and T4 around. So it turns out, if you do that and work through these reality properties of these functions in this, all that does is it changes this plus sign to a minus sign. Okay, so this H4 tilde is just got a minus sign in this overall phase. And so the net result is that if you compute this correlation function, which is the commutator square, which is the sum of H4 plus H4 tilde, then you get that it has an overall factor which is got a cosine appearing in. Okay. And then everything else is identical. So I just write that as gamma R, gamma. Okay, W. The same arguments. It all works out exactly the same. Okay, and I've missed a C. Okay. So what's the punchline? Well, there's this factor guaranteed by these phases in which the commutator square is smaller than the out of time order correlation function in magnitude by this factor that depends on cosine of beta times the Lyapunov exponent over 4. So hence this commutator, the commutator square is suppressed relative to the OTOC by a factor cosine beta 0 lambda over 4. So this vanishes for maximal chaos. Okay, so this is all in the paper by Kitaev and Su. Okay, so what's going on here is exactly as I said. When this is maximal chaos, I think this factor here is an I, and then for H4 tilde, it's minus I. There's exponential growth in both H4 and H4 tilde. They precisely will cancel against each other when you have maximal chaos. And the relative size of the exponential growth in the commutator square relative to the out of time order correlation function is actually telling you the deviation of your Lyapunov exponent from maximal chaos. So this, I think, is, if you work it out, is going to be sine beta 0 over 4 times delta lambda, where delta lambda is the deviation between your Lyapunov exponent and maximal chaos. There might be a minus sign wrong there, but hopefully that's relatively clear. Good. So is it okay for me to carry on for 5 more minutes to tell you the holography story? It will literally be 5.
Yeah, no problem. You have time.
Good, because basically something very similar happens in holography. That's all I really want to say. But this was a new result due to us, so it'd be nice to mention how it happens. So the point I want to finally end on as a final example is this happens also in holographic theories. So in particular, a new result we were able to prove in our paper is that for any configuration of these operators, these commutator squares I've defined are identically 0 at leading order in 1 over n if you have a holographic system dual to classical gravity. And to get something non-zero, to get a non-zero C, you have to include string theory corrections. Actually, scattering, bulk scattering, which involves stringy modes, needs string theory scattering. So the argument I'm going to give for this is incredibly simple. It was very simple. I'm just going to do it very sketchily. So please don't. The details are the important part of the argument is here, but this is very much a sketch of an argument. So in holography, you typically, okay, we have higher dimensional systems, so we also have space. So for consistency, for definition, our out-of-time order correlation function will be something like this. Technically, to define it, I need to regulate this in some way. Let's assume I do that by separating the operators in time a small amount. And the basic point is that we know well how to compute this in holography. So in holography, this is computed as just essentially some two-particle bulk scattering process. So this can be computed in holography as a two-particle bulk scattering process. And the formula for what this thing looks like is quite simple. I'm going to sketch the important things and be very sketchy here. But essentially, it looks like it looks like the exponential of some phase shift for the scattering process, multiplied by some bulk to boundary wave functions, the details of which do not matter for this talk. So essentially, these bulk to boundary wave functions propagate these operators, turn them into quanta on the horizon. They then have some scattering process at the horizon of the black hole, which is described by this phase shift delta of S and X. So let me define that. So delta of S and X is the phase shift for the bulk scattering. Here, S is the center of mass energy for the collision, and it basically is proportional to e to the 2 pi t times t, where t is the time separation of the operators. And okay, roughly speaking, x here is actually the impact parameter, the separation of the particles as they collide near the horizon of the black hole. But roughly speaking, you can think of that as being the separation of these operators in the boundary theory in this case. Okay, so S is the center of mass energy for the collision. Okay. So what's the point? Well, the point is that if you have a theory dual to classical gravity, there's a simple rule for computing this gravitational scattering amplitude, the phase shift for gravitational scattering. It's this collision that people do to compute chaos in holographic theories, where you solve for a gravitational shockwave solution, and this phase shift delta turns out to be the on-shell action of a solution with two shockwaves. Okay, so the basic point is that for theories dual to classical gravity, which is when you have a maximally chaotic system, then this delta of Sx is the on-shell action of some shockwave, of shockwaves. And the point, all that matters about this is it's real. It's some gravitational action evaluated on the solution to the equations of motion. You get a real answer. That's all that matters. Okay, and this results. The fact that this delta is real is what results. It means the scattering process is unitary. This results in, if you compute these commutator squares, you'll find they have to be 0 at leading order in 1/n. Just from this fact, this is real. So let me end by explaining how that works, because it's very similar to the argument I just gave, the Kitaev argument. So I mentioned a few minutes ago this h4 tilde, the other correlation function in the commutator squared, is the complex conjugate of the first one, but where we swap around some time on the operators. And again, all that does is turn that phase into a negative phase. Okay. So if you do that, you just get that this h4 tilde is e to the minus I delta Sx times the same. If you do it carefully, nothing changes with the bulk to boundary wave functions. There's a step to show that, but it's true. And to leading order, and then this will result in this fact. Okay. So in particular, to leading order in 1/n, okay, this phase shift is proportional to 1/n. And so to work to leading order, which is what we always do, you have to expand these exponentials. So if I expand these exponentials, it's probably not too hard to see that gives that this out of time ordered correlation function is essentially proportional to the gravitational phase shift, whereas the commutator squares are essentially proportional to the imaginary part of the phase shift. Okay, so a simple argument shows that the commutator squares probe the imaginary part of the phase shift, not and H4 contains everything. And so again, if you have gravitational scattering where this is real, this commutator square is therefore 0 in any holographic system dual to classical gravity. Okay. So how do you get a non-zero commutator square? Well, you have to move to a non-maximally chaotic system, which in holography means you have to include string theory corrections. And those string theory corrections to the scattering process between these particles, you get a contribution from that the string theory scattering gives rise to both gives rise to an imaginary part of this phase shift, and at the same time it reduces this Lyapunov exponent. So string theory corrections give you a non-maximally chaotic system, and they actually allow this commutator square to be non-zero. But the commutator being non-zero is actually a direct probe of the stringy nature of the scattering, and the gravitational scattering doesn't contribute at all to this commutator squares. So to get C not equal to 0, you need stringy scattering, which results in non-maximal chaos. Good. So that's all I wanted to say. The basic point is we have this hydrodynamic theory, which we now know is a theory of maximal chaos, and it also predicts that these commutator squares vanish. So we thought that was a problem when we discovered that, but it turns out actually that's exactly what you would want an effective theory of maximal chaos to do, because this cancellation of these of the exponential growth in these commutator squares is a defining feature of it seems to be a defining feature of maximally chaotic systems. Katayev has called it coherent scrambling. My interpretation of why coherent is that I'm not sure if this is exactly what is meant by it, but the fact that you have these two exponential pieces cancel against each other like they're perfectly out of phase, the word coherent seems very appropriate for that. And I think the fact that you have this cancellation of exponential growth in these commutator squares, which is what we see in our effective theory, is really telling us something deep about the nature of chaos in maximally chaotic systems. And I think that's something very interesting to try and understand further exactly what it means in the future. So I'll end there.
Thanks a lot, Mike. Very nice presentation. Let's have some time. We have some time for questions. So please go ahead. Whoever wants to ask a question, just unmute yourself. Don't make me go to the second part of the question sessions where I stop recording.
Sure.
Okay.
Can I ask a question, Daniel?
Yeah, go ahead.
Oh, Mike, thanks for the talk. My question is, if we, for example, ignore about the second part of your talk, I mean, the suppression of commutator square,
yeah.
Then considering delta lambda, I mean, the deviation from the maximally chaotic case, we know in the recent work by Choi, Meze, and Sorisi, something like that has been observed, a non-maximally chaotic case. Then I want to understand what does this delta lambda map to in your construction, in your theory? For example, to a broken symmetry or to a case in which something from energy is exchanged between. Okay, please.
So that's a great question. I don't know how to build an effective theory of a non-maximally chaotic system. So in a non-maximally chaotic system, you get an exchange through the stress tensor, which essentially this theory would still describe the stress tensor contribution to the alpha time order correlation function. You then get exchanges of higher spin modes. And I guess there's a question. The question is, could you somehow resum all those contributions into some effective theory that parameterized the contributions of the stress tensor and all the higher spin modes to a chaotic system, to the alpha time order correlator? And I don't know of a way to do that. So the answer is, I would say I can't. At the moment, we can't move away from our theory by changing the Lyapunov exponent away from the maximal value. We don't know how to do that at all. So that is a very good question. I know other people have thought about it as well. Who, I think Felix and Moshe told me they thought about this at some point as well. I don't know of a way to adapt this effective theory yet to be a non-maximally chaotic system. However, the work you're talking about, I think, on this large QSYK model, I think is the way is the clue. But I haven't looked at it yet in enough detail to see what it might lead, what it might suggest. So yeah, I don't know what it would. In our theory at the moment, it doesn't have it. We can't extend it to non-maximal case.
Okay, thank you.
More questions before I stop recording? Okay.
Can I ask a question?
Yeah, yes, of course.
Yeah. Hi. So you said that the deviation from the maximal chaos is stringy correction. Is that 1/n correction in prehistory language?
No, it's an alpha prime correction.
It's alpha prime correction. So
I think
in the dual piece theory, if you have, then it is, I think it is 1/n.
I think it's something like, I don't think it's 1/0. I don't think it's 1/n, but I may be wrong. I don't think it's 1/n. I think
so. It might be something more complicated than 1/n correction in the field theory.
Yeah, I think it's a Tufts coupling correction.
Mm-hmm. It's Tufts coupling correction.
Yeah.
Okay.
Tufts coupling correction.
Then there are several holographic theories which claim the finite coupling corrections, like Gauss-Bonnet or yeah. And do you expect you can see non-maximal chaos behavior in such theories?
That's a great question. The answer is definitely no. So higher corrections to gravity are maximally chaotic, and those systems would still be described by this theory. So in that case, what happens is essentially that's the string theory interactions are essentially just that's the string theory corrections essentially renormalizing the effective action for the stress tensor. And those corrections are included in this theory. What's not included are interactions between the operators mediated by a stringy mode, not by a gravitational mode. So it's not supergravity corrections. It's proper. Yeah, I don't know the best way to say this. It's not those types of string theory corrections. It's the bulk particles scattering off each other through string theory scattering, not through gravitational scattering. So this theory would work for say holographic systems with higher derivative gravity. It's not Einstein gravity that's important. It's classical gravity.
I see. Thank you.
More questions? Okay. Let me thank Mike again and reminding you that we have a talk next week by Matti Järvinen in 1 week from now. Now let me stop recording.